So welcome everyone. So this is another session of the JHU-IITD SMaRT seminar series, which is a joint initiative of IIT Delhi and Johns Hopkins, where we actually bring researchers working on the intersection of scientific machine learning, computational science, and mechanics. So today it's my great pleasure to introduce Dr. Shubhangi Bansude. She's an assistant professor at the Department of Mechanical Engineering at IIT Gandhinagar. She also did her BTech from IIT Gandhinagar. So I think after that, she worked for some time, and then she did a PhD from the School of Mechanical Aerospace and Manufacturing Engineering at the University of Connecticut in 2023, followed by her postdoctoral appointment at the Argonne National Laboratory until 2025. So during her doctoral studies, she was awarded the prestigious General Electric Graduate Fellowship for Innovation, and she also served as a graduate teaching fellow in the UConn School of Engineering. And before her research career, as I was saying, she also worked as an application engineer in Siemens PLM software, that is between 2014 and 2017, where she contributed to advanced CFD solutions for automotive and OEM industries. So her current research right now brings together turbulent combustion modeling, combustion chemical kinetics, and scientific machine learning with a focus towards large eddy simulations and data-driven modeling for reacting flows. So with that, please join me in welcoming Dr. Shubhangi Bansude to this JHU-IITD SMaRT seminar. Thank you so much, Shubhangi, for joining in. Over to you.
Thank you very much for the introduction, and also thank you for inviting me for the seminar. I feel this is a really good platform. So I'll just go ahead and share my slides. Just let me know if you can see them.
Yes, we can see your screen. If you can go full. Yes, that's good. That's great.
Okay. All right. So
yes.
Good evening, good morning, everyone. So I guess I can get started. So again, just a reiteration of introduction. So I'm Shubhangi. I'm currently, okay, I'm sorry. I think I'm sharing the wrong presentation. Just give me a second. I had to change my machine. Sorry, can you see my presentation now?
Yes, now I can.
Okay, perfect. I'm sorry about. Yes, right now I'm an assistant professor at the Department of Mechanical Engineering at IIT Gandhinagar. So I joined in March. It's been almost 7 months now. So as Professor Arti was saying, I just want to highlight here that my research domains are more into and fidelity simulations of combustion systems like gas turbines and detonation engines, and also developing models for targeted physics like chemistry, turbulent combustion, as well as on the diagnostic side. So that's like overview. But today I'll be mostly focusing on my PhD work, where I tried to use machine learning as a tool to advance the turbulent combustion modeling for the larger simulations of these reacting systems. So with that, I would like to just do a brief overview of the talk. So first, I'll start with a brief introduction of what it means to do like turbulent combustion modeling, and go to details of how I use neural ODs for the chemical kinetics integration, as well as develop deep learning based filter density function models. Share with you my thoughts on where research directions are and what are the open problems in the community. So with that, let me start with a very basic question: why still study combustion? So as you know, more than 82% of energy still comes from some kind of combustion of fossil fuels or oil, gas, and coals, and that because it's one of the most reliable sources of energy that we know of. But it is also the biggest concern for the emissions and it is also causing irreversible damage to the climate. Having considered this, there is still a lot of need for improvement when it comes to designing better combustion technologies and also exploring more disruptive technologies with alternative fuels or some combustion regimes like detonation engines. So, with that in mind, this is where computational modeling can be very helpful to accelerate the design and optimization because it can give you insights into the underlying physics of how, let's say, mixing and chemical reactions are interacting with each other, how they're affecting the combustion efficiency, and so on. But one of the challenges with the computational modeling of such reacting flows is that to model these simulation or to in a way that we resolve the necessary spatial and temporal scales that are required to make these decisions, it's still a very challenging task. And just to give you an example, this is a simulation, large Eddy simulation of one of the very small turbofan engines called DGen 380. And to simulate 1 millisecond of physical time, it required about 180,000 core CPU hours, and the cell count that was involved in the simulation just for the compressor and the combustion chamber part, it was 1.4 million cells. So that's about 1.4 billion cells. So you can get an idea about how challenging these simulations are. And this is where my motivation of my work comes from. So coming to the computational modeling of these flows, they can be briefly categorized into three. One is the direct numerical simulation, where we try to resolve all the scales of the turbulence. So as you can see from this plot here, so basically we compute all the scales of the turbulence. On the other hand, we have Reynolds average Navier-Stokes equation, where the idea is to solve for time averaged equation. So you get an estimate of how the time average flow field looks like. And this has been the standard in industry for quite a few decades now. So although it gives you an overall picture of what's going on, it cannot uh, give us information about, let's say, a transient phenomena like instabilities in combustion processes. So this is where LES can be very helpful because it offers us a middle ground between RANS and DNS. So in LES, we only compute the bigger scales, which are battery, and the smaller scales, also known as like subgrid scale, that is like below the grid that we use in LES, that has to be model with some kind of modeling. So this is what the idea of turbulence combustion modeling is. So now just coming to the equation, because this is going to be relevant for the talk. So I would like to just briefly go over that. So when we are talking about doing like a DNS, so what we are technically doing is solving continuity, momentum, and then species transport equation along with equation of state to basically calculate all these details. And we really fine grid and also really tiny time steps to capture this details in DNS. So when we talk about LES, LES involves like spatially filtering these fields. So to develop equation LES, we have to also spatially filter these equations here. And after filtering, this is how the equations looks like. And they look very similar to the DNS equation, but now we have this additional terms that come into account. So what is happening here is, let's say if I'm looking at this location here in the at one particular location in that DNS solution. So in the black is the velocity signal, let's say for at the DNS. And then what we are resolving in LES is this orange signal, which is just capturing the bigger vortices and bigger structures, and the effects of this smaller scale are kind of encapsulated into these terms. And the idea of so now we need models to models for these terms. So the first term in the momentum equation is the SGS stress term. Then this M term here, which is in the scalar equation, that is called scalar flux. And finally, we have a reaction source term. Now, so there have been a lot of now approaches to how to model this term, but my focus uh, in my work is mostly on modeling this reaction system, because that's one of the challenges. So usually when we do simulations with the flat rate chemistry, this chemistry or chemical source term is described by a set of Arrhenius equation. Just to give an example, hydrogen combustion would have at least 10 species, and evolution of each species is governed by certain rates. And if you look at the rates, they are of this form. They take like this Arrhenius kind of the formulation, Arrhenius formulation. So as you can see, it's a highly nonlinear term, and given that we will have a lot of species, they also evolve on different time scales. So that also introduces stiffness in the process. Modeling these terms become the biggest bottleneck in these simulations. So this is where filter density based functions have been quite successful to model this term accurately. But to understand what filter density function is, we have to look at from a statistical point of view. So for example, let's say I have here a DNS of a simple mixing layer, where the temperature, like high temperature region on the top and the lower temperature region on the bottom is getting mixed. So I just removed some cells from the top and the bottom just to give you how the interface of mixing looks like. But let's say if we have a domain and we know everything about like all the scales involved in this in this domain. So and if you're looking at this location x comma t, and let's say we know, and since we have all the information of about how these fields are distributed, this is just a zoomed in view of that. So let's say if we know how the temperature is distributed within that domain, the idea is we can construct some kind of density function based on these values. And once we know the density function, then it is easy to calculate all these filter values and also like higher order of that. So this is the idea of like filter density function. So how we apply this in reacting flows is, so in the previous slide, I talked about the species and energy transport equation, and after filtering, we got this closure problem. But in the filter density function approach, instead of solving for that equation, we solve for the joint PDF of the thermochemical quantity that involves the species mixture fraction, temperature, and sometimes their reactions as well, depending on the formulation. But the idea here is very similar to what I was describing with the temperature. So if you know the filter density function of all these variables together, then we can get these average reaction rates or directly like averaged or filtered quantities directly from that filter density function. And this approach of solving filter density function with this equation, it's called transported FTF. Although this is one of the most accurate like that we have to model the turbulent combustion interaction, it is also very expensive. And one part of talk is going to talk about like how neural ODs can be helpful in accelerating this solution methodology. On the other hand, we have simplified version of the FDF, that is presume FDF methodology, where we model this average variables with some tabulated chemistry as a function of some characteristic variables like mixture fraction and progress variable. But we need to have we need to assume some kind of a probability density function of these variables to get the filter values. And traditionally, the beta PDF has been used as a like a standard. So in my work, I've tried to investigate if we can come up with a better deep learning based models which of the similar complexity that can increase the accuracy of this approach. So with that, I'll start with the first topic, that neural ODs for the chemical kinetics. So the filter density function that I was referring to, this actually it looks like this. And it's very difficult to solve this equation like in this form. So the way it is done, it is with hybrid Eulerian Lagrangian approach, where each cell of like let's say CFD in a finite volume formulation is introduced with a set of stochastic particles, and then we construct a set of stochastic differential equation in such a way that the ensemble average of let's say thermochemical state of each particle, that gives us the estimate of the average values. So this each particle is governed by these two equations here. First equation is to track the position of the particle, and the second is to track the thermochemical composition of a particle. And once we know what this phi alpha plus is for all the particles, we just do the ensemble averaging to get those filtered values. So that's a typical filterative approach. And this particular integration here is was the most expensive step in computationally. So the idea was so use of neural ODEs, the use of neural ODEs to further this problem was inspired by this. For the filter, for the specifically for the filter density function methodology. But then when you look at the equation, I can also write it in a very generic form because this also appears in other turbulent combustion models. And the way usually this is solved is with the operator splitting, and that's because when we try to solve this in a coupled manner, it is stiff equation because here m is representing the mixing source term, and omega is representing the chemical reaction source term, and m can be dependent on the type of flow that you have, so it is very case specific. But omega is what comes from the defined chemical reactions, so that is usually independent of your case. So, and mixing, the timelines associated with this mixing phenomena caused by, let's say, convection or molecular mixing, they are of order of few microseconds. And on the other hand, the chemical system has time scales associated with it ranging from few nanosecond to few milliseconds. So, due to this disparate time scales, this is a stiff system to solve, and the typical way to do it is using operator splitting, where we split the equation into two for some certain, like a global time step delta t, where we first only start with the initial condition, let's say Pt, and assume that the reactions are frozen and do the integration for mixing. And then from the intermediate step, then we go the intermediate step, then we assume that the mixing is frozen, and then we do the reactions. So so the idea is if we can accelerate the integration of chemical kinetics, that accelerates the whole methodology of this transportative. So now coming to the state of the art, this is just it's not a comprehensive overview, but it's just indicative of what kind of methods have been tried for this problem. So solving this equation now also translates to learning a model that goes from Pt to P delta. So conventionally, this has been done with lookup tables, either by storing this integrals before we do the simulation or doing them on the. But in either case, you still have to do like an integration of the system. Coming to the data-driven models, like most of the early work is focused on using artificial neural networks just to replace the tabulated chemistry. But in recent years now, there have been a progress with like other approaches like physics-informed neural networks and resonance. But still, neural ODE has a special advantage because they can work with the they can work with the highly like adaptive ODE solvers. So just coming to that, then here I've just given a like a simple example to understand how the other approaches are different from neural ODEs. So let's say if we have a system and we are going from some initial condition of ZT0 to ZT1, and so in typical or maybe a machine learning modeling approach, so what we are trying to do is trying to learn the difference between these two, or in other words, we are trying to learn the residue. So, and if you look at this, it also appears like a simple Euler solver for solving like a ODE. So that is one of the simplest ODE solver that we have. And the neural ODE take this idea to another level, where instead of learning that residual, we're trying to learn the governing equation itself. And that way, the what we are trying to learn is just this integral, and we are delegating the integration to some other adaptive ODE solver that we already know how to do. So that also that has certain advantages. One, it makes your model a little more compact because you are trying to learn ODE, the derivative instead of the functional relationship between the dynamic system, and it also allows you to, once it is trained, you can use any ODE solver that you want to get this integral. And also, because we are using adaptive time step, there is no constraint on the data to be equally spaced for training. So there are certain advantages with neural ODs. So that is why we use neural ODs for this problem. And in a typical neural ODE training, um, so the forward pass is calculated with this step here, and the now, as you can see, the loss will also have this integration. So to calculate the derivative of loss with respect to the free parameters, the original authors, the authors of the original paper, they have introduced this adjoint sensitivity analysis. So that makes this whole framework of neural ODE quite useful for modeling dynamic system. So now coming back to the problem of chemical kinetics. So one of the challenges was how to make this, how to train this model, because do we do the DNS to get this data, or there is other way? So the way we have approached this problem is by looking at the equation, and we can observe that this is also an equation for evolution of constant pressure reactor. So so the way we generated data is by providing different initial conditions, and then sampling the data from all these data sets. So the usual data set will have, so for the concept, I've used hydrogen air mechanism with 10 species. So for each case, we'll have the, the evolution of all these species with respect to time, and every consecutive data point on the trajectory will act as a training data point. So this is how the data was generated, and we also did some normalization to make sure that all the input parameters are in the similar range, so that it stabilizes the training, and that has also helped with the um, uh, that has also helped the faster convergence. So so the typical training looks like it. So you have an initial condition phi I, and the expected value of the integral is going to be this list phi bar. And so first we feed the data to the neural network, and the neural network is passed through the ODE solver based on the integration you specify, and that gives you a prediction of the integral value at the next time step. And then you can calculate the loss. So this completes one cycle of forward propagation. And then for the backward propagation, we have to go through the ODE solver and adjust the network ways to minimize this error. But even so, one thing that we particularly did for this network was use the explicit solver, and this allowed us to learn the non-step representation of chemistry. And what is the final output of this is just this box here, which can be interpreted as approximation to the source term. And once the training was done, now this can be used in as a replacement for reaction source term in any application. So just first proof of concept was demonstrated with the same reactor with different initial conditions, where we only specified the initial condition, then neural ODE was used as a source term, and it automatically predicts the next time step, and so on. And as you can see, these plots here, they show the trajectory of temperature and few minor and major species for changing initial equivalence ratio and temperature. And and the lines is what we get by directly integrating the detailed chemistry, and the symbols is what we get the neural ODEs. And neural ODEs are doing a pretty good job in capturing the dynamics of the system, and they are also the ignition delay and the equilibrium temperature is also well captured in all these cases. But the next interesting thing was how will it so what is the reason behind this? And we also observed that it was much faster. So then we investigated a little bit into what exactly is giving us that speed up. So for that, we looked at the normal CPU time here, with where the neural ODEs were integrated with different ODE solvers like implicit ODE solver BDF, the hybrid solver LSOD, and the explicit solver IK45. So the So plot here that shows the CPU time for all these cases. The red one is the detailed chemistry, which is also stiff. So that's why we had to use implicit solver to get the solution. And red is basically the detailed chemistry, and we use that as a reference. So as you can see, despite of whatever solver we choose, the neural ODs always have lower number of functional evaluation, and this is because the learned system is non-stiff. But coming to the CPU time, it was observed that the maybe the model that we have chosen, the each function evaluation was slightly more expensive than the detailed chemistry, and that's why you see that in some of the cases the CPU time for uh, these evaluation for neural OD is slightly higher than this. So the final conclusion here is that we learned the non-stiff representation of the chemistry with the neural ODs, and if we were able to integrate it with explicit OD solver, and that gave us about 3 times speed up for this constant pressure reactor cases. But the next question that we're trying to ask is, will it work when we have a mixing terminate? And for that, we performed more test in something called pairwise mixing stirred reactor. So the physics of pairwise mixing stirred reactor is very similar to like one cell in 3D ABS FDF simulation, where we have an incoming fuel oxidizer and also some pilot steam to let the fuel oxidizer ignite. And then we have a bunch of stochastic particles evolving with these set of equation. So each particle also at every time it mixes with the neighbor, and it also reacts based on the reaction system. And then there is also this time scale called pairing, where these two particles which are evolving with these two equations, the partners are changed like abruptly. That introduces some more discontinuity to the system, and also gives us a wider thermochemical space to test our model on. And this has been previously also used to assess the capacity of other turbulent combustion models. So we went with this case, and we performed like multiple simulations with varying this mixing time scale, pairing time scale, and also the residence time scale, which decides how much time fuel and oxidizers will have in the reactor to react. So, and the way we perform the assessment here is, so we used a similar operator splitting method, but for here mixing, for doing the mixing integration, this is a simple equation, so we can actually derive the analytical solution for this. So for every time step, we will do the mixing, and then from the intermediate step, we'll do the reaction. So first set of simulations were done with directly integrating the chemistry, and the second set of simulation was with the neural ODEs. And then we looked at the results. So these are some of the representative results from the cases. So as you can see again, this plot shows the ensemble average temperature and species mixture fractions for the neural ODE, and the here we can see they show the instantaneous temperature of all the particles and how they evolve with time. So you can see that there is a match between the instantaneous values and also on the ensemble average values. So later we perform some more tests by changing the chemical, changing the mixture fractions at the inlet, and or changing the mixing and pairing time scales. And what you see here is on the right, you have the neural OD prediction for changing, let's say, a mixture fraction. And the lines are the average values, and they are superimposed with the RMS value of the temperature. So as you can see, even while changing chemical time scale by changing the mixture fraction or changing the mixing time scale, so the dynamics is again well captured by the neural ODEs compared to the detailed chemistry. So it doesn't just capture the mean, right, but it also does a very good job of um, uh, simulating that stochastic behavior, and that can only be possible if the model is working well for all these stochastic particles starting at various like initial points in that thermochemical space. And now looking at the numerical efficiency of neural ODs for this case with mixing, coupled mixing, we observed that the results were even more encouraging because the speed up that we got in terms of CPU time and also the reduction in error. That was consistent with the previous cases, but in fact, as we increased the number of particles in these tests, the speed up went even higher. So, it's a number of integration that you would require to do one PMSR simulation. It is of order of 10 power 4 to 10 power 6, which is equivalent to like one time step, let's say, in CFD. So these results were very encouraging. We could see about 3 to 11 times speed up, depending on the cases under consideration for the neural ODEs. So this is how we use neural ODEs to accelerate this filter density function methodology. So the next part of the talk is it is on a slightly different note. So I would like to just take a pause here and see if you have any questions. Okay,
If you
so
want, maybe I can. Yeah,
there
I
are no
have
questions.
one quick question.
Yes,
Just trying
yes,
to understand. So the main reason why you had introduced the node is to because the entire process of the chemical kinetics and solving the flow equations, it was being slowed down by the chemical kinetics itself, is it?
yes. So in
Okay.
typical simulation, about 80% time goes into just chemistry.
Okay,
Uh,
so they're actually being
yes,
they evolve in the time scale of things, they evolve faster than the dynamics of the flow itself. So you have to solve them continuously, and that takes a lot of time. The chemical kinetics one,
yes,
and
yes,
therefore you kind
that's
of
right.
had a surrogate model which is the node.
Right, that's right.
Okay, I see. I see. Okay, fine. Yeah. Thanks. Thanks a
Okay,
lot. So I'll have questions
yeah,
later.
yeah. Okay, so now starting with the second part. So now earlier this transported FDF methodology, it requires like solving for the species in the mechanism. So for example, again, my hydrogen mechanism would have like 10 species at the least. Um, and there is a low fidelity counterpart to filter density function is this uh, presumed filter density function model. And the idea here is that for some of the cases, for example, near equilibrium frame, the chemistry simplifies to only simplifies, and then it can be represented as only few characteristic variables. And most of the time, that variable is mixture fraction, especially for non-premixed frame. Then the idea is that we can do some 1D, 0D frame simulations and quantify or tabulate how the thermochemical state and the reaction source term evolve with respect to that characteristic variable, and then just tabulate it priorly. And then during the simulation, we just assume that this particular characteristic variable, it takes some form of uh, uh, like some form of distribution, and we just assume that, and then we use this kind integral to get average values. Now, typically, beta beta function has been used as a surrogate for this assumed FTF model in literature. So, and what we do in that approach is this beta. So, when we are talking about RANS, it is a beta PDF, but when we are talking in context of filtered LES, it becomes a filter density function. The whole idea of using beta as a filter density function is coming from the RANS. But the fact of the matter is, if the PDF in RANS, it represents a very different physics than the FTF in LES. So RANS, we are talking about the the time evolution of that variable, and in LES we are talking about how the variable that variable is distributed within the given space or that filtering length. So that was the assumption people usually like. So that was the assumption for beta as a FDF model, and that is defined based on two parameters. It's a filtered mean of the mixture fraction and the variance of the mixture fraction. So instead of solving finite rate chemistry for all the species, in the presumed FDF approach, we only solve for mean and variance of the mixture fraction, and based on that, we define we basically get the beta distribution. So depending on these two values, you get all these different shapes. And we use information along with the tabulated chemistry to get the closure for a chemical reaction. So the question that we were trying to answer is, uh, so with the same level of complexity, can we get a better model using deep learning to represent these FDFs? So this was a very simple problem, and I have used very simple architecture for this. And the reason we wanted to keep it simple, because the more parameters that you add to your inputs, then you will have to solve those many governing equations in CFD. So the idea was keeping complexity of that input dimension same, but coming up with a better model. And again, the first was, how do you generate a training for this kind of problem? So we used non-reacting constant density mixing layer, because mixture fraction scalar, so the behavior does not change with reactions. And the DNS of these mixing layer kind of the mixing kind of simulations is doable on small scale computer as well. So that's why we used mixing layer as a sample problem here. And the way we generated the data is based on the similar concept that I introduced while talking about what the FTF was. So we did the DNS, then we fixed the LES size to be 6 times that of DNS, and whatever and the distribution of a mixture fraction that you can find at the particular location, that can give you what is the variance, and also a discretized version of the filter density function. And then we just move this box around to all the values of like x and t in all the direction to generate more and more filter density functions. And we used a very simple mixing layer, the non-premix mixing layer, like a which evolves in time to collect this set like filter density functions. And then we use a simple MLP architecture to where your mean and mixture fraction input, and the probabilities are the output. So this was just rephrased as a multi-class regression problem, or like a regression problem with multiple outputs. And so this and another experiment that we did is, because DNS in this case we did it for the mixing layer, but it is still like an expensive process. So can we use the data from low fidelity reactors like this PMSR, which essentially has a similar physics, but with a different approach to generate the similar kind of data and train the same network to get and compare the results of these two. So in DNS, we are getting the filter density function data from the all these the spatial distribution of the variables itself. But in PMSR, the approach is slightly different. It's more Lagrangian. So what we did is just change the input mixture fractions and see how the PDF of mixture fraction evolves in this PMSR. And we did these simulations for a range of time scales that were seen in DNS to generate a similar kind of data set. And then from that data set, we trained a model for FTF. So interestingly, when we looked at like how much of sample size is required to train a model to reduce the bias and also variance in the training, and we used Jensen Shannon divergence as the metrics to evaluate how this for the evaluation to compare the two probability distribution. And one interesting thing that we saw is, even though the data is coming from different type of data set, the complexity of the problem remains the same, because the based on bias variance training and testing curves for different training sample sizes, the optimal training data set that we found for the cases were of the same order. And looking at the results, there were some typical, like these are some of the typical filter density functions shapes that we gathered. And the observation was when the fuel and air they are not mixed at all, that would give like a delta distribution, or they are completely mixed, in which case you get a Gaussian kind of distribution. That in that case, the beta was also doing a very good job. But when then there were more complicated or complex shapes like this multimodal distribution, the models trained on DNS as well as PMSR, they were doing a better job. So this was a priori validation, and then we also implemented this in our in-house LES FDF code to perform more testing. So some of the tests, so are the summary of the tests that we have done. So since the model was only trained on constant density mixing layer, because the idea was to just learn how the FTF of the scalar mixture fraction evolves. The first test was conducted on the variable density mixing layer. We also changed the grid and filter sizes of the LES to see if the model is still valid. And in the last, we also assisted performance to filter the nonlinear function, because that is what is most important for the reacting cases. So we did simulations. So here, this is a very like outline of framework, how these models were integrated into like a CFD solver. So in the CFD solver, solve for the hydrodynamic equations like continuity and momentum. And then there is a turbulence model that is coming into picture to model that is stress system. And then we added this module, DNA and FTF module, and the tabulated history was also given as an input. And this basically comes together to get the average values of, let's say, variables like temperature, mixture fraction, and also RT here, which is it's a specific enthalpy. You can interpret it as a specific enthalpy. And then we did, so the way we did was, this was a very comprehensive comparison. So what we did is we compared the results from the finite difference, where we actually solved the mean and variance of the mixture fraction with the predictions of DNA models, and also with the beta FDF model. And then we also did transported FDF simulations, because this would give us like a fidelity somewhere between DNS and the beta FDF. And we did this comprehensive comparison for different cases. So what we see is it's the distribution of mixture fraction at the center plane of the domain at steady state. And here we also have a scatter plots to give an idea about how the model is doing for all the cells at that particular time. And so as you can see, both the models which are trained on DNS as well as PMR, they were able to predict distribution pretty. So the scalars, they show pretty good match. And also looking at the scalar plots, the scatter plots, you see that they do a very good job capturing the FTF shapes and on cells within that domain. Similarly, we looked at the variance of the mixture fraction as well. And so when it comes to variance, the correlation was not that great compared to the mean value, but it is still does a very good job compared to the beta FDF, which tends to fail when the value of the variance is low or like high. So this was just a like a comparison, very exhaustive comparison of the DNN models with the filter density function as well as Monte Carlo and DNS. And we did some testing by changing the grid size and filter sizes as well. So this was case where the grid is 2 times like finer compared to the base case, but then we changed the filter sizes. If the filter size is same, because filter size is basically giving you what is the effect of the SGS scales within that filter size. As you can see, the 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 profile has not changed much. It is very similar to the previous cases. We can still see these big rollers, and but when we go to the filter size, which is half of the baseline, we can see that it starts capturing the smaller and smaller details. So the first column here that shows the results from finite difference, where we solve the equation for mean directly, and these two are the column 2 and 3 are the predictions of machine learning models or DNN models. And as you can see, they can also work very well when you change the size. as well. And that is essentially because whatever information is needed to define maybe that the FTF is already embedded into the variables. And that is why we feel like model which was only trained on one single case works pretty well for the other cases as well. So here are again just uh, some of the results from the variance comparison, and as you can see, it also shows us like a similar performance. And then coming to filtering the nonlinear function, we tried it for filtering a scalar dissipation rate, which is usually given as a function of a mixture fraction like phi here, and it looks something like this, and also like a reaction rate, reaction source term. So the first column here shows you if you don't have any model, which is if you just define uh, the filtered value of that um, scalar dissipation rate with just scalar dissipation rate evaluated at the filter value of mixture fraction, it will always like over predict. But deep neural network based models are doing a better job at capturing. They are able to filter the values pretty accurately for the non-reacting as well as the reacting cases. So with that, I would just like to like summarize what I have discussed. With these two cases, I have tried to what I've tried to do here is use the deep learning to accelerate the simulations of transported FTF simulations, which are kind of high fidelity model to the model the turbulent combustion problems. And we are also showing that how deep learning can be used to increase the accuracy of low fidelity models. So for the neural ODEs, the extensive comparison we have done for different cases, we see that the neural ODE results are quite accurate compared to the detailed chemistry. And the model that we independently develop with zero-D reactors can be coupled with mixing. And neural ODEs, they learn the non-state representation of chemistry, and that helps us get some speed up compared to the direct integration of chemistry. And on the presumed FTF front, compare the results of DNN models with respect to existing practice of using beta FTF as well as the Monte Carlo simulations. They were able to predict this Fourier density functions quite accurately, and also were able to filter the nonlinear function, and hence can be applied to reacting flows directly. So with that, so this was mostly part of my PhD research, and since then I have after that I went to work in Argonne, so I slightly changed my trajectory. Now I'm back to working on these problems. So one of the things that is actually from these two models is the domain knowledge. And I think to make these models more generalizable and also reduce the complexity of the underlying models, we need to embed what we know about the physics, including the mass or energy conservation principles and invariance principles and so on. So we have a lot of work to do in that direction. And also we can also simplify some of these processes by embedding our understanding of physics into data curation and designing network architecture or loss functions. This is where I think some work needs to be done. So I have just highlighted some of the cases here where it has been shown that especially in terms of embedding physics, it can be either embedded as a like function, which is also like a soft constraint, and also a hard constraint where you can change the architecture or design an architecture in a way that you kind of embed this constraints as a hard or a strong constraint. And this particular study here that very well highlights that how the models where we have a hard embedding of the physics constraints can work very well for the multi-scale systems like combustion. And also we can easily also couple this neural ODEs with reduced order models to further accelerate it. But then then the question becomes that if this the learned late representation can be interpreted. So I think we are also as a community should be working more towards more interpretable and explainable model, and this will be very useful when we use these models in applications like fire safety or studying the instabilities in the cluster level. And apart from that, I also feel like the models also should be generalizable. That is something that we need to think about how we can make it, and that's where the question of computational complexity also comes into picture. Because how data for making your models more generalizable. So because doing DNS is always not possible. So are there any other ways where we can use our knowledge, or like a domain knowledge, to create ways to also have more efficient training data generation and learning processes? And the last two are they are more of a generic comments. We also need a benchmark data sets where we can develop and test our models. So as a community, I think we should, that will also accelerate the development and implementation of these techniques in scientific computing. So with that, I think I would like to end here. But if you would like to learn more about these problems, I think Professor Amy from Stanford University have written a very nice review paper that you can refer to, where he really nicely discusses some of these challenges in detail. That is a pretty good read. So with that, I'll just stop here and just the last comment. So now I've started working at IIT Gandhinagar, and I've established this computational combustion and machine learning laboratory, which works at the intersection of fluid dynamics, combustion, machine learning, and numerical methods. So the focus is on developing fundamental models to model turbulence chemistry and turbulence chemistry interaction, and also do integrate them in with the existing tools or traditional methods to do high fidelity simulations of applications like gas turbines, scramjets, and detonation engine. So if you are interested, please visit the website, and I also have a post position open. So if you are interested, feel free to apply. Okay, so with that, I'm open for questions. Thank you.
Thanks a lot, Shubhangi, for the nice presentation. So now we have the floor open to questions from the participants.
Maybe I can start, Rasdeep?
Yes, okay, please, yes.
Okay. Hi, Shubhangi. Thank you so much for the presentation. It was wonderful. So, although I don't share a lot of overlap with the work, but there is some bit of overlap which comes from my postdoctoral, when I was doing my postdoc. And that was the first part of your work. So what I wanted to understand in the neural OD part that you did did you use different network training for each of your species, or was it like all the species were learned with one network?
All the species were learned with one network, and this was a very challenging problem to start with, because the fact that again every species evolves at a different time scale. So what helped in that is regularizing the training data itself. So just using a simple transform like minmax, or uh, uh, just transforming it based on the mean and variance of the data itself, that helped a lot in training.
I see. So back in that day, I mean, I have I have a work which is on latent neural operators, and in that particular work, I actually tried working on a stiff chemical kinetics problem, uh, and I found it really challenging to actually like manage all the scales together for all the species. And what I did is to find out a low dimension representation of the whole of all the species at a particular timestamp, and I evolved the latent representation over time. And then eventually, when I was at the time step which I needed, I used again the inverse of the low dimension representation to get back to the physical space.
I have to say, I think that is a natural progression to the work that I have shown. I think, and that is actually currently what I'm working on. So two
I
things.
see.
One is because as this is a nitrogen mechanism, but as we are moving towards the let's say more complex fuels like mixture of so right now mixture of methane and hydrogen, then the detailed mechanism like 53 species. So handling 53 species with vanilla neural OD is not going to be helpful. So I think that's where we are exploring this option of dimensionality reduction and also trying to embed physical constraints that we know of, like element conservation, mass conservation, and also enthalpy constraints. So that is exactly what we're working right now.
I see. I see. And we also have some work from one of my students. I am not sure if he's online. Oh, yeah, I see he's online. So, one of my student has recently worked on a time integrator neural operator where he's trying to march in time, and he's also trying to couple it with a latent representation, which might be of your interest at some point. So, when we have it out, I'll definitely share it with you.
Yeah, definitely, definitely. I think yeah, that's a really good suggestion. I definitely check it out. Thank you very much.
Yeah, yeah, yeah. Thank you so much. This was a very insightful presentation today. We can have more questions from the audience.
So I have one question. Okay. So they, yeah, Divya, please go ahead.
If you go ahead.
Uh, Hello. Hi, Professor Shubhangi. Thank you for the very nice presentation. I wanted to ask about the neural OD work. So you mentioned that you took a hydrogen air, like the Lee mechanism, right, for like describing the finite rate, chemistry.
Mm-hmm.
So what is the pressure range that you worked on? Like,
Okay, so this yes, so the focus was incompressible gas turbines when I started this project. So we have only used one pressure. Uh, but again, right now what I'm working on is extending this methodology for high speed applications like scramjets. So that's where I am also looking to integrate a pressure level, different pressure levels as well. But right
okay,
now for these studies, it was just one single pressure.
okay. So. Uh, as far as like to the best of my knowledge, if you go to high pressures like around 10 bar, you'll start seeing other species also having more contributions like H2O2. So let's say I actually wanted to ask if you want to operate with multiple pressure levels, do you think a single neural OD will be able to handle it, or you would want because hydrogen
Mhm.
has a typical S shaped curve, right? So uh,
Right.
do you like, would you recommend having multiple neural ODs to handle that, or you think a single neural OD can handle
Mhm.
both the behaviors, I would say?
So to again, uh, so I don't have a clear answer for that, but I so my intuition is if we go with a reduced order representation, like if we somehow have a mechanism of finding latent dimension for the system, it would be able to handle multiple pressures as well, because then pressure becomes like another variable. So right now, what I
Yeah,
have is all the 9 species and a temperature as the input, and then the pressure
yeah,
will
yeah.
also be part of it, right?
Right,
So
right,
my understanding is if we can, yes, if we go into a latent, latent representation chemistry, I think we should be able to handle it. But if we were to do it again as a just a single network without any dimensionality reduction, it might be difficult to learn that underlying chemical source term for all these pressures together. So it might be more beneficial to go with the multiple networks. But I would
right,
still, as a CFD person, I would still prefer to have one single network that is working for all the operating conditions. Because we are using this network in the ODE solver, right? So every time there is a function call, it's going to come and evaluate the source terms there. So
right,
having multiple networks would add some overhead. So
right.
my preference would be to go with a single network that can like work well with all the operating pressures. And I think embedding physics would definitely help with this, because models become more generalizable when we have this like physics constraint, physics embedded as a constraint into the neural network.
Right, right.
So that's my
Yeah,
take on it. Yeah.
yeah. Okay, thank you.
So yeah, I have this question regarding the second part of your presentation. So I just wanted to understand that the second part of the presentation you had the LES, and you wanted, so because LES was only kind of doing the large scales, so the smaller scales you were actually missing out, and you were, so what were
Yes.
you trying to do with the FDF there? So like the smaller scales that are missed out, you still want to kind of somehow
Mhm.
get some kind of a probabilistic behavior on them.
Right. So let's say, so the easy way to understand it is, if you're doing a DNS, then you would know what is the reaction source term for all the cells, right? But for LES, we can only calculate that reaction source term for that only one temperature, which is the resolved temperature or resolved species, right? But we don't know how is the distribution, how is the that turbulent chemistry interaction coming into picture, because if you don't assume that PDF, you're just assuming that it's a delta function. So we can easily evaluate that nonlinear function only on a single value. Then that single value will be the resolve field from the LES. That is why we need FTF, or the that distribution. And as I mentioned briefly, it's usually the beta. That's a very widely used approach. Like we just assume it to be a beta FTF. Uh, yes.
So
I
is
hope
that,
that answers your question.
yeah, so if you assume it to be a beta function, right? It's a beta distribution. Uh, like, so it means that it would only have a single mode, right? So can the distribution, I'm like
So
trying to
beta
think that,
distribution, yes, beta function is defined on two parameters. So it is, and depending on these two parameters, it can take different shapes. If we consider a very simple case where fuel is in that singlet, where the fuel is coming from the top and the oxidizer is coming from the bottom. So usually the mixture fraction tells you how much of like fuel is contained in that particular stream, let's say, and then the fuel would have z equal to 1, oxidizer will have z equal to 0. And if you're looking at uh, the density distribution in the vicinity of those areas, it's just going to be a delta PDF, that's it. But when the mixing is happening, then it
hmm,
will have some distribution, right? And that is characterized with the mean and the variance of distribution within that small cell. So what we do is we solve the equation for mean and variance, because mixture fraction is eventually it's a physical quantity. We can derive a governing equation for that. So the ideally what we do is, along with our momentum pressure, like a continuity momentum equation, we also solve for this mean and variance. And based on these two values for every cell at every time stem, we get what the beta distribution looks like. So in terms of implementation, it's more of a discrete operation. Uh,
hmm.
but so that's how it comes into picture.
Okay, I see. Okay. So it's basically like the way that you're missing out on certain, like the lower scales, you're trying to model it is it using a probability density function, and then using that to
Right.
kind of make up for the things that you've missed. Is that a correct way to say?
Yes, that's right. Yeah, that's the correct way to interpret it. Yes.
Okay, great. So because of this filter density function that you're using, so you're actually also inducing a probability density function on the output as well. Is it not? Or you're only
Uh,
working with the mean and the covariance, is it? A mean and the
yes,
variance.
we're only working with the mean because that is what we are interested in. This
Only
the
working with the
resolve
mean.
quantity looks like. Right, right.
Okay. Okay. So if you had also continued with the variance, you would have also gotten some uncertainty about the solution, isn't it?
That is something that I haven't done any uncertainty analysis, because the focus of study, if we can come up with the more accurate model for the same level of complexity, and the other one was, can we use 0D react data from 0D reactors to build these models that will also work for like large scale simulations.
I see. So I was
So
just trying to think of
yes,
it from a point of view of a stochastic correction term, right?
right.
So If you
Mm-hmm.
essentially, it's kind of a stochastic correction term for not being able to kind of resolve at all scales. So you're having some scales and then
Mm-hmm.
you're missing out on some other smaller scales, and you're using a stochastic
Mm-hmm.
corrective term, which is kind of going to also give you a stochastic distribution on the output, which you're only interested in the mean in this case, I believe, right?
Right.
Yeah.
Yes.
Okay.
Right.
Okay. Yeah. Thanks. Thanks a lot. So any other questions from other participants?
We're already over time, Rajiv. I think
Okay,
they
I see. Yeah.
probably that's one reason.
I think then you can actually close it, I think, from Sunata.
Okay, sure.
Yeah.
So thank you, Shubhangi, for joining us today. And this was really very great presentation. And thank you everyone for tuning in. We'll see you all next week at the same time. Thank you.
Thank you
Thank
all.
you very much. Have a
Bye.
nice day and have a nice evening, people in India. Yeah. Bye.
You too. Bye.